Our universe holds more planets than there are grains of sand on every beach. For centuries, that profound question of whether we are alone has haunted us. Now, we are closer than ever to an answer, thanks to the discovery of worlds beyond our solar system. Scientists hunt for these exoplanets by looking for a few key ingredients: a place not too hot and not too cold where liquid water could pool. By the end of this journey, you will know the top 30 most promising planets where life might exist right now. We will explore worlds with global oceans under hazy skies and planets bathed in the perpetual glow of 3 suns. Which of these distant shores feels most like home to you? Our journey begins with a world cloaked in a steamy haze. K2-18b is not a rocky planet like our own, but a mysterious sub-Neptune, a type of world larger than Earth but smaller than the ice giants in our solar system. Its thick atmosphere is rich in hydrogen, and beneath that shroud, astronomers believe a vast, global ocean might exist. This is what scientists call a Hycean world, a place where the endless sea is not of liquid water as we know it, but a superheated, high-pressure ocean that could span the entire planet. While this environment would be instantly lethal to us, it presents a perfect, stable home for microbial life, the kind that thrives in Earth's most extreme deep-sea vents. It whispers the possibility that the most common abodes for life in the cosmos might not be Earth-like spheres at all, but these strange, water-dominated realms. Far from that shrouded ocean, we find the outer sentinel of a famous family. TRAPPIST-1H is the 7th and farthest known planet from its tiny, cool star in the TRAPPIST-1 system. At this great distance, its surface should be a frozen wasteland, too cold for liquid water. Yet, this world holds a secret source of warmth. The gravitational pull from its 6 sibling planets constantly tugs and squeezes TRAPPIST-1H's interior. This process, known as tidal heating, could generate enough energy to melt ice deep underground, creating a hidden, subsurface ocean insulated from the frigid surface. It is a reminder that life does not always need a sunny beach. It can flourish in the dark, warmed from within by the silent, rhythmic dance of celestial mechanics. Then there is a world that feels almost familiar. Kepler-1649c is an exoplanet that sends a shiver of recognition across the light years. It is almost exactly the same size as our own planet, and it orbits squarely within the habitable zone of its red dwarf star. This delicate positioning means it receives a similar amount of stellar energy as Earth does from the Sun, raising the tantalizing possibility of a temperate climate. While we know little about its atmosphere, its size and location make it one of the most Earth-like worlds ever discovered by the Kepler telescope. It stands as a powerful symbol in our search, a hint that planets with conditions reminiscent of our own pale blue dot might be scattered throughout the galaxy, waiting to be found. Our cosmic neighborhood holds a world just 4.2 light-years away. Proxima Centauri b is the closest known exoplanet to Earth, a rocky world orbiting within the habitable zone of its star. But this star is a tempestuous red dwarf, and the planet is likely tidally locked. One side faces the star in perpetual, scorching daylight, while the other is trapped in an eternal, deep freeze. The thin strip of land between these two extremes, the Terminator line, could be the only place where temperatures are just right for liquid water. Yet life would face constant threats from violent stellar flares, which could strip away any atmosphere and bathe the surface in harmful radiation. Survival here would mean thriving underground or beneath a global ocean, turning this nearby world into a paradox of both immense promise and profound peril. Not far in the cosmic scheme of things lies another intriguing target, LHS-1140b. This is a super-Earth, a planet significantly more massive than our own but still potentially rocky. Astronomers are locked in a debate over its true nature. Is it a vast water world, a globe completely enveloped by a deep, planet-wide ocean? Or does it possess a thick, gaseous envelope like a mini Neptune? Recent observations lean toward a rocky composition with a dense atmosphere, which could be a powerful shield against its star's radiation. If it is a water world, its entire surface would be a single, dark abyssal plain, a realm where life could exist around hydrothermal vents, completely isolated from the sunless sky above. Then we have a world that feels like a glimpse into Earth's own distant future. Kepler 452b orbits a star remarkably similar to our Sun, and it has done so for 6 billion years. That is 1.5 billion years longer than Earth has existed. This older cousin resides comfortably in its star's habitable zone, giving it ample time for life to not only emerge but to potentially evolve into complex, even intelligent, forms. What wonders might have developed on a world that has enjoyed such stability for so long? Its longer history presents a captivating thought experiment, suggesting that we might be the newcomers in a galaxy where ancient, sophisticated civilizations could already be looking back at us. Some planets bask in the glow of a single sun, but JWST experiences a sky dominated by three. This super-Earth orbits within the habitable zone of its primary star, a red dwarf, while two other suns dance in its heavens. Depending on their alignment, days could be lit by a single star, two, or all three at once, casting complex and ever-changing shadows. This celestial ballet raises profound questions about the nature of life, forcing us to consider how biology might adapt to such an unpredictable cycle of light and darkness. Could vegetation evolve to photosynthesize under multiple, distinct spectra of starlight? It is a world where the very definition of a day is fluid, challenging our Earth-centric views of habitability. Another early beacon of hope in the exoplanet hunt was Kepler 22b. It was one of the first worlds confirmed to orbit within its star's habitable zone, a milestone that sent waves of excitement through the scientific community. The central mystery surrounding this planet is its composition. Is it a rocky super-Earth, a place with continents and oceans, or is it a gaseous mini-Neptune, a world with no solid surface at all, only deepening layers of cloud and crushing pressure? The answer remains elusive, a reminder that finding a world in the right place is only the first step. We must then determine if it is a place where life could actually take root, or just a beautiful, barren illusion. Much closer to home, at least on a galactic scale, lies the Tau Ceti system. The planet Tau Ceti e orbits a sun-like star just 12 light-years away, a stone's throw in cosmic terms. But its promising location comes with a critical caveat. It sits on the inner, warmer edge of the habitable zone. This precarious position creates two starkly different possibilities. It could be a super-Venus, a hellish world choked with greenhouse gases and scarred by volcanic activity, where lead would melt on the surface. Or, if it possesses a protective atmosphere with just the right composition, it could moderate the intense heat and maintain vast, warm oceans. This single planet embodies the fine line between a habitable paradise and an uninhabitable furnace, a testament to how delicate the cosmic recipe for life truly is. A quiet, ancient star just 12 light-years away hosts a world that mirrors our own in remarkable ways. Teegarden Star B boasts one of the highest Earth Similarity Index scores ever recorded. This small, dim red dwarf has burned for billions of years, far longer than our Sun, offering a profoundly stable environment. Its gentle, quiet nature means it rarely erupts in the violent flares that plague other red dwarfs, providing a calm and constant light for its orbiting planet. Life here would not need to hide from stellar tantrums, but could instead potentially develop on the surface, basking in the permanent, deep red twilight of its aged sun. This world suggests that some of the most life-friendly real estate in the galaxy might be found circling these old, serene stars. Much further out, in the constellation of Lyra, another kind of world awaits. Kepler 62f is smaller than Earth and orbits in the cooler, outer reaches of its star's habitable zone. Astronomers believe it is almost certainly a water world, a globe completely encased in a deep, global ocean. With no land in sight, the only solid ground would be at the very bottom of the sea, near hydrothermal vents spewing mineral-rich warmth into the eternal darkness. Life here would be purely aquatic, a universe contained within a single planet-wide sea, where evolution might follow a path completely alien to our own land-based experience. It is a reminder that a habitable world does not need continents to be alive. Then we have a neighbor with a precarious existence. Wolf 1061c is located in one of the closest planetary systems to Earth, a mere 14 light-years away. This super-Earth orbits dangerously close to its star, walking a razor's edge between habitability and a runaway greenhouse effect. A little too much atmosphere, and the planet would trap immense heat, turning into a scorching hellscape like Venus. But with just the right atmospheric composition and pressure, it could maintain a temperate climate, with liquid water pooling on its surface. This delicate balance makes it a fascinating subject of study, a world whose entire fate hinges on the precise thickness and chemistry of its air, proving that location is only one part of a much more complex equation for life. The search for life often leads us into scientific debates, and few worlds have been as controversial as JJ581g. Its very existence was questioned for years, with some astronomers arguing the data was just a ghost in the signal. But if it is real, this super-Earth is a tantalizing prize. It orbits squarely within its star's habitable zone, and its gravity is likely strong enough to hold onto a substantial atmosphere. The planet is also probably tidally locked, creating that same stark division between a scorching day side and a frozen night side. Yet within that permanent twilight belt, conditions could be surprisingly Earth-like, with the potential for vast, calm seas. It stands as a powerful reminder that our methods of discovery are still evolving, and the most promising worlds sometimes hide just at the edge of our perception. Far from that dispute, we find a world with a more certain but equally fascinating orbit. HD 40307G is a super-Earth that completes a journey around its star in about 200 days. That year is not so different from our own, painting a picture of a familiar orbital rhythm. Located within its star's habitable zone, this planet might have the right temperature for liquid water, but its habitability hinges on a critical unknown, its atmosphere. With a mass several times that of Earth, its surface gravity would be much stronger. Walking on this world would feel like carrying a tremendous weight, a force that would also profoundly shape the nature of its air and any potential oceans. Could life adapt to such crushing pressure, building biology that is sturdier and more resilient than anything we know? Then came a discovery that changed everything. Kepler 186f was the first rocky planet we ever found that was almost exactly Earth's size, orbiting peacefully within the habitable zone of its own star. This was not a larger super-Earth or a smaller mini-Neptune. It was a peer, a world that demonstrated conclusively that planets like ours are not rare cosmic flukes. Kepler 186f orbits a red dwarf star, so its sunlight would be a dim, perpetual red hue. Any plant life on its surface might evolve to photosynthesize using those crimson wavelengths, potentially covering the landscape in shades of black or deep purple to absorb every possible photon. This planet was a milestone, a definitive proof that the core ingredients for an Earth-like world are scattered throughout the galaxy, waiting on countless shores for the spark of life to ignite. Hope can be a fragile thing in the cosmos. Kepler 438b was once our greatest beacon, a world with an Earth similarity index higher than any other known planet. It was the closest thing we had found to a true twin, a rocky world nestled perfectly in its star's habitable zone. But then came a sobering discovery. Its red dwarf star is a tempestuous beast, frequently unleashing superflares of radiation hundreds of times more powerful than anything our Sun produces. These stellar eruptions likely battered Kepler 438b, potentially stripping away its entire atmosphere and scouring its surface bare. This world transformed in our eyes from a potential paradise into a cautionary tale, a reminder that a planet's star is just as important as the planet itself in the story of life. Within the same triple star system as its sibling we discussed earlier, JJ667cf offers a different kind of puzzle. This super-Earth also orbits within the habitable zone, adding to the celestial dance around its primary star. But its potential hinges entirely on what it is made of. Is it a dense, rocky world with a solid surface, or is it a water world shrouded in a thick, steamy atmosphere? The presence of two other suns complicates its climate, but also enriches its possibilities. The gentle, combined warmth from multiple stars could help maintain a stable temperature, even on a world that might otherwise be too cold. JJ667cf challenges us to broaden our definition of a habitable environment, suggesting that complex stellar families can create pockets of stability where life might find a way. And then we have the crown jewel of the famed TRAPPIST-1 system, Planet E. Of the 7 rocky worlds orbiting that ultra-cool dwarf, TRAPPIST-1e stands out. Its density tells us it is almost certainly a rocky world like Mars or Earth, and it orbits squarely in the middle of the star's habitable zone. This positioning gives it the perfect temperature, in theory, for vast oceans of liquid water to exist on its surface. Because the star is so faint and close, the planet is likely tidally locked, presenting a world of extremes. Yet models suggest that a thick enough atmosphere could distribute heat around the globe, creating a surprisingly temperate environment. This combination of confirmed rock, the right temperature, and potential for water makes TRAPPIST-1e one of the most important planets we have ever found. It is not just a candidate for life. It is a primary target for the next generation of telescopes, which will peer into its atmosphere, searching for the telltale signs of biological activity, the breath of another living world. Kepler 442b receives a gentle, filtered light from its star, about 70% of what Earth enjoys. This soft illumination could be the perfect energy for a very familiar process, photosynthesis. While its red sun would cast a dim, crimson glow, plants on this world might not need to be the deep black or purple of other red dwarf planets. With more light available, alien flora could potentially display a stunning array of colors, perhaps even shades of yellow or orange, as they adapt to harness the specific wavelengths of their sun. This world is not just about temperature. It is about the quality of light itself, offering a canvas for an entire ecosystem to paint itself in hues we can scarcely imagine. Shifting our gaze, we find a world that promises answers. K23d orbits a star much brighter than the faint red dwarfs that host so many of our candidates. This brilliant sun makes the planet a prime target for the most powerful space telescope ever built, the James Webb Space Telescope. As K23d passes in front of its star, the telescope can analyze the starlight filtering through its atmosphere. Scientists will be looking for the chemical fingerprints of water vapor, methane, and oxygen, the very building blocks and potential waste products of life. This world is not just a candidate. It is a laboratory, a place where the first concrete evidence for life beyond Earth might be found not in some distant future, but within our own lifetime. Then there is a world of profound quiet. Ross 128b orbits a red dwarf that is remarkably calm and stable, especially when compared to the stormy tantrums of Proxima Centauri. This gentle star bathes its planet in a steady, unwavering light, free from the sterilizing radiation flares that blast its more famous neighbor. The surface of Ross 128b could be a far more hospitable place, where an atmosphere has a chance to persist, and life on the surface would not need to seek constant shelter. It represents a different kind of hope, one based not on sheer proximity or Earth-like size, but on the simple, enduring peace offered by a benevolent sun. These 3 worlds each offer a unique pathway to life, from the quality of its light, to the clarity of its air, to the profound stability of its home. A planet caught between two identities presents a fascinating puzzle. Kepler 1638b orbits comfortably within its star's habitable zone, but its size places it in a mysterious category, larger than Earth yet smaller than Neptune. Is it a massive rocky super-Earth, a world with vast continents and deep oceans, or is it a mini-gas giant, a place with no solid surface at all, only endless, swirling clouds that gradually compress into a hot, fluid core? The answer defines everything about its potential for life. If it is rocky, its stronger gravity could hold onto a thick, protective atmosphere, creating a stable environment. But if it is gaseous, any chance for life as we know it likely vanishes into the depths. This world embodies the central challenge of exoplanet science, reminding us that being in the right place is only the beginning of the story. Just 12 light-years away, a steady beacon has burned for eons. Lytan star is one of our closest stellar neighbors, and its planet, Lytan b, is a super-Earth firmly within the habitable zone. What makes this world so compelling is the profound stability of its sun. This ancient red dwarf has a lifespan measured in trillions of years, a timescale so vast it dwarfs the entire history of our universe. If life emerged on Lytan b, it would have had more than enough time to not only take root but to evolve into forms of staggering complexity, all under the constant, deep red glow of a star that will barely change for eons to come. This world offers the promise of continuity, a stage where the drama of life could play out over cosmic epochs without the threat of its sun fading or flaring into oblivion. Further out, in the constellation of Cassiopeia, another super-Earth hints at a chilly potential. HD 219134G was discovered not by watching for a star to dim, but by measuring its subtle wobble, a technique called radial velocity. This method revealed a world orbiting in the colder, outer region of its system, a place where liquid water could only exist under very specific conditions. If this planet possesses a thick, hydrogen-rich atmosphere, the resulting powerful greenhouse effect could trap enough heat to warm its surface, creating a temperate environment despite its distant orbit. It is a world whose habitability is written in the air, a reminder that a planet's atmosphere can transform a frozen wasteland into a potential oasis, rewriting the rules of where life might be found. Deep within the celebrated TRAPPIST-1 system, another world holds its own secrets. TRAPPIST-1F is a colder sibling, orbiting further out from its dim star than the more famous planet E. This distance likely gives it a surface of solid ice, a frozen crust that might stretch across the entire globe. Yet beneath that icy shell, something remarkable could be stirring. The gravitational pull from its neighboring planets could be flexing TRAPPIST-1F's core, generating internal heat through tidal forces. This energy might be enough to maintain a vast, liquid ocean trapped between the frozen surface and the rocky seafloor below. It is a world that mirrors Jupiter's moon Europa, a dark, aquatic realm where life could thrive completely isolated from the universe above, sustained by hydrothermal vents on an alien seafloor. Shifting our gaze across the galaxy, we find a world that mirrors our own in two crucial ways. Kepler 1229b is a super-Earth that receives almost the exact same amount of energy from its red dwarf star as Earth does from the Sun. This stellar flux, a measure of warmth and light, is strikingly similar, suggesting surface temperatures could be remarkably Earth-like. The planet's size also points toward a rocky composition, completing a profile that feels hauntingly familiar. While its red sun would paint the sky a perpetual crimson, the fundamental conditions for liquid water are met. This combination of familiar size and familiar warmth makes Kepler 1229b one of the most compelling Earth analogs we have discovered, a world where the ingredients for life appear to be assembled with a known recipe. Finally, we encounter a system where two worlds share the potential for life. Kepler 283c is a planet that sits comfortably within its star's habitable zone, but its story is made richer by its family. It shares its solar system with an inner planet, Kepler 283b, which orbits too close to the star to be habitable. The presence of multiple planets in a single system is a thrilling find for astrobiologists. It suggests that the entire Kepler 283 system had ample material to form rocky worlds, increasing the odds that at least one of them, Planet C, ended up in the perfect spot for life to emerge. This world reminds us that we are not just searching for single planets, but for entire planetary families where the cosmic dice were rolled more than once, dramatically improving the chances for a living world to be dealt into existence. 31 light-years from Earth, a super-Earth named JJ357d offers a different kind of promise. Its mass suggests a rocky world, perhaps twice the size of our own, orbiting squarely within its star's habitable zone. A planet of this scale could possess a powerful gravitational field, one strong enough to hold onto a thick, nurturing atmosphere. With that dense blanket of air, JJ357d could effectively trap the faint warmth from its red dwarf star, creating a greenhouse effect that raises surface temperatures just enough for rivers and oceans to flow. Without an atmosphere, it would be a frozen rock, but with one, it transforms into a potential water world, all within our cosmic neighborhood. This proximity makes it a jewel for future observation. When next-generation telescopes finally peer into its skies, they will scan for the chemical signatures of water vapor, methane, and other gases that could hint at a living, breathing world. It is a profound thought that a potentially habitable planet, a place where life could have taken root, is orbiting a star so close we can almost point to it in the sky. The fate of JJ357d is written in its atmosphere. Climate models paint two strikingly different portraits of this nearby world. With a thin or non-existent atmosphere, it would be a frozen snowball, its potential for life locked away beneath miles of glacial ice. But if it possesses a thick, dense blanket of air, rich in greenhouse gases like carbon dioxide, everything changes. That atmospheric coat could trap the faint warmth of its red sun, creating a powerful greenhouse effect that transforms the entire planet. In this scenario, JJ357d could be a temperate, water-rich world, a place where oceans ripple under a deep red sky. This single variable, the thickness of its air, holds the power to determine whether this world is a barren icebox or a living oasis. Given its likely tidal lock, one side forever facing its star, the most habitable real estate might be a narrow ribbon of land. This is the Terminator line, the eternal boundary between day and night. Here, the sun would perpetually sit on the horizon, casting a soft, twilight glow across a landscape of rolling hills and shallow seas. In this band of constant dusk, temperatures could be mild and stable, a perfect sanctuary for liquid water to pool and flow. Life here would never know the cycle of sunrise and sunset, but would exist in a world of permanent, gentle illumination. What kind of life could cling to existence in such a place? We can look to the darkest corners of our own planet for clues. Around deep-sea hydrothermal vents on Earth, entire ecosystems thrive in complete darkness, powered not by sunlight but by chemical energy from the planet's core. On JJ357d, similar communities could exist in a global ocean, their biology built around the warmth and minerals seeping from the seafloor. On the surface within the Terminator zone, plants might evolve to be intensely black to absorb every possible photon from the dim red sun. Or perhaps life would forego photosynthesis entirely, finding other, stranger ways to harvest energy from its stable twilight world. This nearby super-Earth challenges us to envision biospheres that operate on a completely different set of rules, proving that life is not a delicate flower, but a tenacious force that can take root in the most unexpected of skies. Moving closer to the faint red heart of the TRAPPIST-1 system, we encounter TRAPPIST-1d, a world balancing on a razor's edge. Positioned as the third planet from its star, it receives a gentle but constant drizzle of stellar energy, slightly more than what Earth gets from our Sun. This small, rocky sphere is one of the inner siblings in that remarkable family of 7. Its size and mass point to a solid, terrestrial world, not a gaseous one, but its potential for life is written in the air, or what might be left of it. A thick atmosphere could be this planet's saving grace. Winds could carry the warmth from its perpetual day side across the globe, preventing the scorching heat from concentrating and instead creating a more uniform, temperate climate. This atmospheric circulation could turn a world of extremes into a planet with stable, liquid water. Yet this same atmosphere holds a terrifying risk. With its star so close, TRAPPIST-1d is constantly bathed in a higher level of radiation. If its atmospheric blanket is too effective at trapping heat, the planet could easily tip into a runaway greenhouse effect. The oceans would boil, the rocks would bake, and this promising world would transform into a hellish twin of Venus, a permanent scar in its solar system. This delicate balance between a nurturing climate and a planetary inferno is precisely what makes TRAPPIST-1d so fascinating to astronomers. It represents a critical test case for how terrestrial planets behave around small, cool stars. When the James Webb Space Telescope turns its gaze toward this system, the atmosphere of TRAPPIST-1d will be a primary target. By analyzing the starlight filtering through its air, we will learn if this world mastered the delicate art of climate control, or if it succumbed to the fire. Its story is a lesson in planetary fragility, a reminder that being rocky and in the right place is only the first step in a much more complex dance for survival. The gravitational pull from its 6 siblings constantly needs the interior of TRAPPIST-1d, a process that generates intense internal heat. This tidal friction could power a world of volcanic activity, with geysers erupting through cracks in the crust and magma churning close to the surface. All this geothermal energy might be more than enough to maintain a vast, global ocean hidden beneath a thick shell of ice, creating a dark, watery sanctuary completely insulated from the conditions above. But the surface itself could also be a place of strange stability. A dense atmosphere, possibly rich in carbon dioxide, might envelop the planet. While this sounds harsh, such an airy blanket could perform a delicate balancing act, scattering just enough stellar radiation to prevent a runaway greenhouse effect while simultaneously trapping sufficient heat to keep water in its liquid state. On the surface, under the dim, cherry-red glow of its sun, shallow seas could lap against rocky shores, their chemistry shaped by the constant volcanic outgassing from below. Life on this world would experience a sky unlike any other. The system's compact architecture means the other 6 planets would frequently transit the Sun, appearing as large, distinct orbs sailing across the crimson disk. These celestial events would cast shifting, complex shadows and create regular, predictable dimmings of the already faint light. For any intelligent beings, these transits would be fundamental to their understanding of the cosmos, perhaps even forming the basis of their calendars, their mythology, and their first steps toward science. They would not need to invent the telescope to discover other worlds. They would simply need to look up at their own extraordinary sky. Kepler 442b emerges from our list not merely as a candidate, but as a frontrunner in the search for another living world. Its distinction rests on a powerful combination of factors that mirror our own planet with uncanny precision. This exoplanet is almost exactly the same size as Earth, a rocky world with the gravity and physical structure needed to hold onto a substantial atmosphere. More importantly, it orbits squarely in the center of its star's habitable zone, a region often called the Goldilocks zone. Here, the temperature is just right for liquid water to exist on the surface, not boiling away into steam or freezing solid into ice. But the true secret to its promise might be the star it calls home. Unlike the turbulent red dwarfs that host so many other candidates, Kepler 442b orbits a stable K-type star, often described as an orange dwarf. These stars are calmer and longer-lived than our own Sun, offering a steady, benevolent light for billions upon billions of years. This stellar stability provides the most precious commodity for life, time. Ample time for the first single-celled organisms to form in a primordial sea, and for evolution to work its slow, patient magic toward complexity. Imagine a world with a familiar nitrogen and oxygen atmosphere, scattering the light of its orange sun across blue skies. Vast oceans could separate continents of rugged, earth-toned rock, a landscape where the fundamental processes of geology and weather feel hauntingly recognizable. While its sunlight is slightly redder and dimmer than ours, it is more than enough to power photosynthesis, potentially covering the land in vegetation adapted to its unique spectrum. Of all the thousands of exoplanets we have found, Kepler 442b scores among the highest on metrics designed to measure Earth similarity. It is not a world of extreme tidal lock or violent stellar flares, not a waterlogged globe or a gaseous enigma. It is, by every measure we currently possess, the closest analog to our own planet we have yet discovered in the cosmos. This makes it arguably the single most promising known candidate for hosting life, not as a bizarre, subsurface shadow, but as a vibrant, surface-dwelling biosphere that we might one day recognize. Yet reaching out to this promising world presents a monumental challenge. Kepler 442b orbits a star more than 1,100 light-years from Earth, a distance so vast it defies human comprehension. We are not seeing this planet as it is today, but as it was over a millennium ago, when the light now reaching our telescopes began its journey across the galaxy. At such an immense distance, the planet is completely lost in the brilliant glare of its star, a firefly sitting directly beside a powerful searchlight. To truly study it, we need more than indirect methods. We need to block out the starlight itself and see the pale blue dot directly. This requires a technological leap, a new generation of space observatories designed with a singular, profound purpose to find life. That future is taking shape with missions like the proposed Habitable Worlds Observatory. This ambitious telescope would use a sophisticated star shade, a giant disk flown in precise formation to cast a deep shadow, artificially creating a cosmic eclipse and allowing the faint light of the planet itself to be captured and analyzed. The goal is not just a picture, but a spectrum, a chemical fingerprint of its atmosphere. Scientists will direct this incredible machine to scan the air of Kepler 442b, searching for the telltale signs that scream of biology. They will hunt for the unstable partnership of oxygen and methane, gases that rapidly destroy each other unless they are constantly replenished by living processes. They will look for the glint of liquid water on its surface, and perhaps even for the red edge, a specific signature in reflected light that on Earth is caused by the way chlorophyll in plants absorbs most visible light but strongly reflects infrared. Finding that single marker would be a discovery for the ages, proof that not only does life exist there, but that it has covered the land in its own unique foliage. A mission to this world would seek to answer the ultimate question: is that familiar-looking planet a true twin? A living, breathing world where forests of alien trees sway under an orange sun? Or is it a beautiful, barren mirror, a reminder of how delicate the flame of life can be? Kepler 442b is more than just a point of data. It is a beacon, a symbol of our deepest hope that in the immense, cold darkness of space, we are not alone. This fundamental rule of habitability guides our entire search. Astronomers call it the circumstellar habitable zone, but its popular name, the Goldilocks zone, perfectly captures its essence. It is that narrow orbital band where conditions are not too hot and not too cold, but just right for liquid water to pool and persist on a planet's surface. Think of our own solar system as a perfect illustration. Venus, shrouded in a thick carbon dioxide atmosphere, orbits too close to the Sun. It experiences a runaway greenhouse effect, with surface temperatures hot enough to melt lead, making liquid water impossible. On the opposite end, Mars orbits too far away in the cold outer reaches. Its thin atmosphere cannot retain enough heat, and any water exists only as permanent ice. Earth, of course, sits perfectly in the middle of this delicate zone, our world a vibrant testament to the power of this cosmic balancing act. Yet the location and stability of this sweet spot are entirely dictated by the star at the center of it all. A massive, brilliant, blue giant star would have a habitable zone that is both incredibly wide and positioned very far out. But such stars burn out in only a few million years, hardly enough time for life to even begin. In contrast, a faint, cool red dwarf has a habitable zone that is narrow and huddled very close to the star. While these stars shine for trillions of years, any planet in that tight orbit faces the threat of tidal locking and violent stellar flares. Our own Sun, a stable, middle-aged G-type star, offers a generous and long-lasting habitable zone, a gift that has allowed life on Earth to flourish for billions of years. The Goldilocks zone is not a guarantee of life, but it is the universe's most promising starting line, the place where the cosmic dice are most likely to roll in favor of a living world. Our quest for life has been anchored by a single, powerful idea, that water is the universal solvent for biology. But perhaps this assumption is a cage of our own making. The chemistry of life might be far more inventive than we ever dreamed, flourishing in environments we would consider utterly hostile. Imagine a world where rivers and lakes are not filled with water, but with liquid methane and ethane, flowing sluggishly across a landscape of frozen water ice. This is not science fiction, it is Saturn's moon Titan, a place where the temperature is so cold that water is as hard as rock. Here, a completely different form of life could potentially exist, one that uses liquid hydrocarbons the way we use water. Its cells might be built with membranes not of lipids, but of sturdy compounds like acrylonite rhyl, forming flexible, stable structures in the deep freeze. Such life would breathe hydrogen instead of oxygen and metabolize acetylene for energy, a biological pathway that would be completely alien to everything on Earth. The very definition of a habitable world expands beyond the Goldilocks zone to include these frozen realms, where the warmth for life comes not from a star, but from the internal heat of a planet or moon. This principle shatters our Earth-centric view and forces us to look at our own solar system with new eyes. Jupiter's moon Europa and Saturn's moon Enceladus are frozen balls of ice, far from the sun's warmth. Yet beneath their icy crusts, vast global oceans of liquid water are believed to churn, kept from freezing by the constant gravitational kneading from their giant parent planets. These are not surface habitats, but dark, subsurface abysses where life could thrive around hydrothermal vents on the seafloor, completely independent of sunlight. The plumes of water vapor erupting from Enceladus offer us a tantalizing sample of that hidden sea, a free ticket to analyze its chemistry without ever landing. If we find life there, it will prove that the universe is teeming with aquatic worlds. They are just hiding their oceans beneath a shell of ice. What if life can even exist without a surface or an ocean at all? The clouds of Venus, with their scorching surface temperatures and crushing pressures, seem like the last place you would look. Yet high in its atmosphere, in a temperate layer of sulfuric acid clouds, some scientists speculate that microbial life could float. These organisms would need to be incredibly resilient, tolerating extreme acidity and harnessing chemical energy from the atmosphere itself. This vision of aerial, acid-dwelling life pushes the boundaries of habitability to the absolute limit. It suggests that a planet does not need to be Earth-like to be alive. It just needs a stable environment, an energy source, and the right chemistry, no matter how strange that chemistry may seem to us. The search for alien life is no longer just about finding another Earth. It is about discovering the universe's full biological potential. A spectrum of life so vast and varied that it might be flourishing in the methane rivers of Titan, in the dark oceans of Europa, and even in the acid clouds of a hellish world, waiting for us to recognize it. Red dwarfs are the silent majority of our galaxy, outnumbering stars like our Sun by more than 3 to 1. This sheer abundance means most of the real estate for planets in the Milky Way orbits these dim, red suns. Their greatest gift to potential life is time. A typical red dwarf can burn steadily for trillions of years, a lifespan so immense it dwarfs the current age of the universe. On a planet circling such a star, evolution would have an almost endless canvas to work with, providing billions of extra years for simple organisms to climb the ladder toward intelligence. But this promise of longevity comes with a steep and dangerous price. The very faintness of a red dwarf forces its habitable zone inward, huddling dangerously close to the star's warmth. At such a tight orbit, a planet becomes tidally locked, with one hemisphere perpetually baked in daylight and the other plunged into eternal, deep freeze night. The only place for moderate temperatures would be a narrow, razor-thin line at the border, a land of permanent twilight where the star forever sits on the horizon. Life here would be confined to this delicate ribbon, never experiencing a true sunrise or sunset. The challenges deepen with the star's temperament. Many red dwarfs are unruly youth, prone to violent tantrums in the form of superflares. These eruptions can unleash torrents of X-rays and ultraviolet radiation, hundreds of times more powerful than anything our Sun produces. A young planet orbiting such a star could have its atmosphere utterly scoured away, its surface sterilized before life ever had a chance to begin. For a world to be habitable around a red dwarf, it needs a perfect set of defenses, a strong magnetic field to deflect radiation, and a thick atmosphere to distribute heat from the day side to the night side, and to shield the surface from stellar fury. The question is not whether these worlds exist, but whether they can survive their sun's turbulent childhood to enjoy its incredibly long, calm adulthood. These red dwarf systems are a cosmic gamble, offering the prize of near immortality, but only to those planets tough enough to endure the storm. This powerful new way of seeing transforms distant points of light into worlds with breathable air. The James Webb Space Telescope is our greatest instrument for this task, a technological marvel that acts as a cosmic chemist. It does not see these planets directly, but studies them through their sun's own glow. As a distant world transits, moving in front of its star, a tiny fraction of that starlight filters through the planet's atmosphere. Different molecules in that alien air absorb specific colors of this light, leaving behind a unique fingerprint in the spectrum. JWST reads these fingerprints, detecting the presence of water vapor, a potential ocean's sigh. It can find carbon dioxide, a sign of a possible terrestrial world, and methane, a gas that on Earth is largely produced by living organisms. Finding these molecules together, especially in unstable combinations, would be a revolutionary hint that something on that world is actively maintaining the atmosphere's chemistry. But to find life itself, we need to go beyond hints and gather undeniable proof. The next great leap is already on the drawing board, the Habitable Worlds Observatory. This future telescope is designed with one audacious goal: to block out the blinding glare of a star and directly see the pale, faint light of an Earth-like planet. It would not just detect chemicals, it would take a picture of another pale blue dot and analyze its surface for signs of a living biosphere. Scientists will search for that dot's unique color signature, looking for a red edge that on our world is caused by vegetation strongly reflecting infrared light. They will hunt for the seasonal ebb and flow of surface colors, the bloom of alien algae in a vast sea, or the telltale gases like oxygen and methane in proportions that can only be explained by biology. This is the final step in our grand quest, moving from identifying promising addresses to knocking on the door and listening for an answer from within. The final proof of life will not be a dramatic image, but a ghostly fingerprint in starlight. Scientists call these clues biosignatures, and they are the chemical whispers of a living world. Think of Earth's own atmosphere as a perfect example. Our air is a chaotic, unstable mixture, filled with gases that should quickly destroy each other. Oxygen is highly reactive, constantly trying to combine with other elements to form stable compounds like rust. Methane, on the other hand, is readily broken apart by sunlight. For both to exist in significant quantities simultaneously, something must be constantly replenishing them. That something is life. Plants and phytoplankton pump out oxygen, while microbes in wetlands and the guts of animals release methane. This persistent chemical disequilibrium is a powerful biosignature, a sign that a planet is not just a barren rock, but a breathing, active biosphere. Beyond this, astronomers will also hunt for other gases like nitrous oxide, or even the faint, collective glow of chlorophyll from alien vegetation covering a continent. A different kind of search listens for signs not of life, but of intelligence. These are technosignatures, the calling cards of a civilization that has mastered its world. They could be narrowband radio signals deliberately broadcast across the galaxy, or the powerful flash of a laser pulse used for interstellar communication. They might even be unintentional, like the telltale signature of industrial pollution in an exoplanet's atmosphere. On Earth, we have chemicals like chlorofluorocarbons, or CFCs, that do not occur naturally and are solely the product of our technology. Detecting a similar synthetic compound in the air of another world would be a staggering discovery, evidence that we are not the only species to have built an industrial society. Some searches even look for megastructures, vast artificial constructions like swarms of solar panels orbiting a star, which would subtly alter the light we observe from that system. Finding a biosignature would tell us that life is a natural cosmic phenomenon, a common spark in the universe's great darkness. It would mean that biology is not a fragile, singular accident on Earth, but a fundamental process that emerges wherever conditions allow. The discovery of a technosignature, however, would carry an even deeper meaning. It would reveal that we are not alone in our consciousness, that another species has looked up at their night sky and asked the same profound questions. It would fundamentally rewrite our understanding of our place in the cosmos, shifting humanity from a solitary voice to a member of a vast, galactic community. The search for these signatures is humanity's greatest experiment, a quest to see if the universe is merely matter and energy, or if it is also somehow alive. So many worlds hold the promise of life, a galaxy seemingly teeming with potential. This very abundance collides with a haunting, silent reality. If the universe is so ripe for life, its silence is a profound and unsettling mystery. This is the core of the Fermi paradox, a simple question with staggering implications. Where is everybody? Physicist Enrico Fermi first posed this during a casual conversation in the 1950s, capturing a puzzle that has only grown more urgent with every new exoplanet we discover. The numbers are overwhelmingly on the side of life. With hundreds of billions of stars in our galaxy, and many of those stars hosting planets, it seems statistically inevitable that intelligent, spacefaring civilizations would have arisen. They would have had billions of years to expand across the Milky Way, colonizing star after star. Their artifacts, their signals, or their ships should be everywhere we look. Yet when we train our telescopes on the cosmos, we are met with nothing but a vast, unbroken quiet. This great silence forces us to confront several unsettling possibilities. One of the most sobering is the Great Filter theory. This idea suggests that there is some kind of barrier, an evolutionary or technological challenge that is nearly impossible for life to overcome. The filter could lie in our past. Perhaps the transition from simple, single-celled life to complex, multicellular organisms is an incredibly rare fluke, a biological lottery that we just happen to win. If this is the case, then the galaxy might be filled with microbial life, but utterly devoid of intelligent beings. The more terrifying prospect is that the great filter awaits us in our future. Maybe every advanced civilization eventually discovers a technology, perhaps in particle physics or artificial intelligence, that inevitably leads to its own destruction. In this scenario, the silence of the cosmos is a grave warning, a collection of tombs for species that reached our level of development and then vanished. Another hypothesis is far more benign, but equally strange. The zoo hypothesis proposes that advanced galactic civilizations are fully aware of our existence, but have chosen to place us in a kind of cosmic quarantine. They observe us from a distance, much like we observe animals in a wildlife preserve, refusing to make contact until we have reached a certain level of maturity or technological wisdom. Our planet would be a designated laboratory, and our sense of solitude would be an illusion maintained by beings far older and more powerful than we can comprehend. A final possibility is that our search is fundamentally flawed. We are listening for radio signals and looking for oxygen, but an intelligence a million years more advanced than ours might not use technology we would even recognize. Their means of communication could be as far beyond our radio telescopes as the internet is beyond smoke signals. They might have transcended biological form entirely, living as digital consciousnesses within vast, planet-sized computers. Their grandest constructions might be invisible to us, built from dark matter or existing in extra dimensions. We could be surrounded by a galactic community, but are like ants in a jungle, unaware of the bustling city just beyond the trees. The silence is not empty. It is filled with questions about our own future. Are we the first to reach this stage, the pioneers of a galaxy soon to be filled with life? Or are we simply the last to arrive, listening for voices that faded into silence eons ago? The answer to the Fermi paradox will tell us not only about our place in the universe, but about the ultimate fate of intelligence itself. The silent question hanging over all these discoveries is how we will ever reach them. Our current rockets are like tiny rafts, utterly inadequate for crossing the ocean of interstellar space. But the human mind is already building the vessels of tomorrow. Consider the audacious vision of Breakthrough Starshot. This project aims to send a fleet of wafer-thin probes, each no bigger than a postage stamp, on a journey to the Alpha Centauri system. They would not carry fuel, but would be propelled by a vast array of powerful Earth-based lasers, their light sails pushed to a significant fraction of light speed. A voyage that would take a conventional spacecraft tens of thousands of years could be reduced to a mere 20. These tiny messengers would scream past Proxima Centauri b in a flash, their cameras snapping pictures as they go, transforming that faint point of light into a real world with clouds, continents, and perhaps even city lights. It is a staggering concept, turning our entire planet into a launch laser to push a butterfly's wing across the void. For human travelers, the challenges are exponentially greater, demanding a shift from spacecraft to world ships. These would be colossal, self-sustaining arcs, carrying entire ecosystems and generations of people, who would be born, live, and die during the millennia-long journey. Their destination would not be their own, but that of their far future descendants. The very structure of human society would have to adapt to the confines of this artificial world, a tiny bubble of life sailing through an endless, star-dusted night. And then there is the dream that rewrites the laws of physics itself, the warp drive. While purely theoretical, some scientists speculate that it might be possible to warp the fabric of spacetime itself, contracting space in front of a ship and expanding it behind. Instead of moving through space, the ship would ride a wave of distorted space, effectively allowing it to travel faster than light without breaking any physical laws. The energy requirements are astronomical, beyond anything we can currently conceive. But the mere fact that such an idea is being seriously explored in physics labs shows the direction of our ambition. These are the bridges we are starting to design, lines drawn on a cosmic map that connect the worlds we have discussed to our own future. We may not lay the stones ourselves, but we are the generation that first charted the course, that turned these alien shores from mathematical probabilities into names, into destinations. Every new planet we add to our catalog is another reason to build the next great telescope, to fire the next powerful laser, to solve the next impossible equation. The journey to these distant worlds begins not with a rocket's ignition, but with a simple, relentless question: what is waiting for us there? From shrouded water worlds to planets bathed in the light of 3 suns, our journey across 30 alien shores reveals a universe of staggering diversity. Each of these distant orbs, from the promising rock of TRAPPIST-1e to the Earth-like perfection of Kepler 442b, tells its own unique story of potential. They are not mere points of light, but entire worlds with their own climates, their own chemistries, and their own hidden possibilities. This incredible variety sends a powerful message. The galaxy is not a barren desert, but a garden rich with planets that hold the fundamental ingredients for life. The sheer number of these candidates suggests that the cosmic recipe for a habitable world is not a rare, secret formula, but a common blueprint written into the fabric of star formation itself. While we have not yet found definitive proof, the evidence points toward a cosmos that is likely teeming with worlds where life could have taken root. The next time you find yourself under a clear night sky, look up at those twinkling stars, pick a single, faint point of light, and remember that it might be the sun for a hidden ocean, a global sea where unknown creatures swim in the dark. Think of the silent, rhythmic dance of planets we have named, each one a testament to the universe's boundless creativity. Our grand adventure of discovery is only just beginning, with new telescopes and technologies poised to peer deeper into the atmospheres of these worlds than ever before. We want to know, which of these 30 planets captured your imagination the most? Was it the nearby promise of Proxima Centauri b, or the ancient stability of Kepler 452b? Share your favorite in the comments below, and if you want to join us for the next journey into the mysteries of space, be sure to subscribe. The greatest discoveries are still waiting just beyond the next star.